Hello students, today my topic of discussion is Power BJT, which comes in the Diploma course of Electronics and Telecommunication Engineering in the 5th semester, and I hope this particular topic will also be helpful for other science and engineering courses in electronics. How can we define a bipolar junction transistor, that is BJT? We can say it is a semiconductor device consisted of 3 layers and it has 3 terminals. The 3 layers are namely emitter, base and collector regions or layers. The 3 terminals are namely E, that is emitter terminal, base, that is B terminal, and the collector, that is C terminal. It is called bipolar. That is, within the name of BJT, the word bipolar is present. Why it is so called? Because both type of carriers, that is electrons and holes, that is both negative and positive carriers, participate in the current conduction process. Thirdly, BJTs can be widely classified into 2 types, NPN and PNP. BJTs find various applications. For example, it can be used in amplifier circuits, switching circuits, oscillators, relay and driver circuit, AC motor speed controller circuit, DC to AC inverter circuit, and so on. An analogy which will describe the operation of a BJT. Here you can see 3 different input terminals are here, or 3 different regions. That is, if we consider the flow of the liquid from this part to this part is actually controlled by this valve. And let us see how it actually works. You can see here that it is actually working when the input from this side is coming. It is actually uplifting this valve. That is, this particular valve is actually controlling this output valve, and depending on that, the amount of the liquid flow actually increases, which specifically denotes that with the increase in the input flow, there will be an increase in the output water flow. In the similar manner, the same thing happens for the BJT. That is, if we consider the common emitter configuration, then obviously IB will be the input current. IB will be the input current. IE is the current from the emitter side. IC is the output current. So, more will be the value of IB, more will be the value of IC. Let us see again. You can see here, that is, you can see as the value, as the water level in the input side is increasing, the output water level is also increasing. Let's understand how a power BJT is different from a low power BJT. The high current carrying capability of a power BJT is the basic difference. A power BJT has high current carrying capability, which is in ampere order, whereas that of a low power BJT is much less. The current gain, beta, of a power BJT is much less than that of a low power BJT. I can say it is one of the important drawbacks of a power BJT. Power BJT has a bigger metal body in order to dissipate heat generated due to the large current flow. Now, let us see the symbolic representations of power BJT. This is the symbolic representation of an NPN bipolar junction transistor. Obviously, it is what I'm showing here, it is the symbolic representations of power BJTs. Here you can see the terminals are base B, collector C and emitter E, and the symbolic representation is exactly similar that you have seen in case of a low power BJT. And it is a symbolic representation of PNP transistor. The terminals are exactly similar, but the arrowhead is inward, and the overall symbolic representation is exactly similar or same that you have seen in case of a low power transistor. Now, let us know about the structure of a power BJT. Like a low power transistor, a power BJT also has three terminals, that is collector C, emitter E, base B, but the structure of a power BJT is different. It has a vertically oriented four-layered structure. If you remember that the structure of a low power transistor, low power BJT, is an horizontal structure, and here the structure is vertically oriented four-layer structure. However, the structure of a low power transistor was consisted of three layers. The vertical structure is made to increase the cross-sectional area of the device. For an NPN transistor, that is, if we consider the NPN transistor's structure, why we are talking about specifically about the NPN transistor? Because for high frequency applications, the switching speed of the device is very important, and the switching speed of an NPN transistor is comparatively much more than that of a PNP transistor. So see the third point, that is, for an NPN transistor, the first layer, which is the top layer, is a heavily doped N plus emitter region. In the plus sign, N plus, that is the plus sign indicates the heavy doping. The second layer is moderately or medium doped base layer. Here I have not put any plus or minus sign because of the moderate doping. The third layer is a lightly doped collector drift region, and here I have put N minus. The minus sign indicates the light doping of this particular region. The fourth layer is a highly doped collector region. That is, I have written here, that is N plus. The plus sign indicates the heavy doping of the region. The use of the collector drift region, that is the N minus layer, increases the voltage blocking capability of the transistor, which is very important. This layer decides the breakdown voltage of the device. However, the disadvantage of this layer is that the increase in the on-state voltages and the increase in the on-state device resistance, which consequently increases the on-state power loss. The power handling capability of power transistors is much larger. As I've already told you that the current carrying capability of a power transistor is much larger. So far, the power handling capability of the power transistor is larger. They dissipate power in the form of heat, due to which the effective area of the power transistor is made larger. Now let us see the structure. Here you can see the structure of an NPN power BJT, and here you can see the three terminals, base, emitter and collector, and you can also see the four layers. As you can see, this is the top layer, N plus region, which is the emitter region. The second top layer, that is actually the base region, N minus region, which is actually the collector drift region, and the N plus region, which is the substrate or the bottom layer, is actually the collector region. Okay. Now let us see the thicknesses, which is very important to know. First one is the thickness of the emitter region, which is 10 micrometer or 10 micron. Secondly, the thickness of the base region, which varies in between 5 to 20 micrometer. Then, the thickness of the collector drift region, which varies in between 50 to 200 micrometer. Then, the thickness of the substrate, which is the collector region, is approximately 250 micron. So it is the overall structure of an NPN transistor, power transistor, and you can see the vertical type of structure of the transistor. Let us see some important points. First point is that the thickness of the base region is made thicker. That is, the base region is made thicker in comparison to the logic level low power transistors in order to increase the breakdown voltage of the device, which is very important point for a power transistor, as a power transistor operates in high voltage applications. So far, the breakdown voltage is required to be large. The breakdown voltage also depends upon the thickness of the collector drift regions. That is, these are the two regions, that is, the base region is comparatively made thicker in comparison to the low power transistors, and at the same time the thickness of the collector drift region also depends upon the breakdown voltage. More we require, more the value of the breakdown voltage, more will be the thickness of the drift region. Secondly, the vertical structure of power BJTs is made as this structure provides the maximum cross-sectional area through which the current, if we consider the current as I, flows within the device, and the current density is generally written as J per unit area becomes minimum. Consequently, the on-state resistance as well as the power loss of the power BJT will be minimized. That is, the vertical structure is one of the solutions that has been made to minimize the power loss of the power BJT. Thirdly, due to the large cross-sectional area, the thermal resistance of the power BJTs becomes low, and the power dissipation problem can be reduced or has been reduced. Now, lastly, the current gain, that is beta, which is actually the ratio of the output current to the input current, and if we consider the configuration to be the CE configuration, it is the ratio of IC, that is the collector current, to IB, that is the base current, and the value of the current gain beta varies in between 5 to 10, which is a drawback of a power BJT, because such a low value of the beta will not help us to make an amplifier circuit. Okay, that's all for today.